All right, now we return finally to the problem of computing eigenvectors and eigenvalues for a linear transformation. These are elements of a vector space V. It's not necessarily Rn. So let's let T from V to V be a linear transformation. To find the eigenvectors and eigenvalues, of T, so that is elements of the vector space such that T of V equals a multiple of itself. We do the following. First, we find the matrix of T. With respect to a natural basis. Let's say B of V. And let's call that matrix A. So we'll find the matrix A of T with respect to a natural basis of V. Then we'll find the eigenvalues and eigenvectors of A using the characteristic equation and systems of equations. Then the eigenvectors of A are the coordinate vectors of the eigenvectors of T, and the eigenvalues of A are the eigenvalues of T. So let's do an example of this whole process. We'll start with a linear transformation, pick a basis of the space, convert it to a matrix, find the eigenvalues and eigenvectors of that matrix, and then translate them back into the language of our original vector space, V. Let's do this with a linear transformation we've considered before. So I'm going to take this linear transformation from week 7, lesson 5. Let's let V be 2 by 2 matrices with trace 0. So that is all the matrices A, B, C, negative A. Trace is the sum of the diagonal entries. So this entry plus that entry has to add up to be 0. That means that they have to be opposites. And then B and C can be anything. So natural basis of this space is 1, 0, 0, negative 1. So we're taking the A out of here, and then the B 1, 0, 1, 0, 0, and then the C 0, 0, 1, 0. So obviously every element of this space, which has that form, can be written as A times this plus B times that plus C times the other thing. And let's let T be the transformation of this vector space that maps a matrix, let me call it M, to the L1 matrix times M minus M times the L1 matrix. Now the matrix of T with respect to B is, we did this in week 7, lesson 5. We found that it was 0, -1, 1, -2, 0, 0, +2, 0, 0. All right, let's call this matrix A. Let's find the eigenvalues of A, the eigenvectors of A, and then figure out what elements of this vector space are the eigenvectors of T. So to find the eigenvalues of A, we'll solve determinant of A minus lambda I equals 0 for lambda. So determinant of, we'll subtract lambda from the diagonal entries, minus lambda, minus lambda, minus lambda, and then copy the other ones, -1, 1, 0, -2, 2, 0. So determinant of that equals 0 tells us that, let's see, negative lambda cubed plus 0 plus 0 minus -2 lambda, so plus 2 lambda, 0 minus -2 lambda, so it's another plus 2 lambda equals 0. So that's negative lambda cubed plus 4 lambda equals 0. And that means that if we factor out a lambda, we've got lambda times negative lambda squared plus 4 equals 0. So if we multiply by -1, maybe it'll be easier to see. Lambda times lambda squared minus 4 equals 0. So that means that lambda times lambda minus 2 times lambda plus 2 equals 0, because lambda squared minus 4 is lambda plus 2 times lambda minus 2. So we have our 3 eigenvalues of A, 0, 2, and -2. Alright, now let's look at the 0 eigenspace of A. So we'll solve A minus 0I V equals the 0 vector. In other words, A times V equals the 0 vector. So here's A. We need 0, -1, 1, -2, 0, 0, 2, 0, 0. So this is the system of equations that has to be equal to 0, 0, 0. And well, we can pretty much solve this without doing any row operations. Because if we let V3 be T, then the first equation says that -V2 plus V3 equals 0. So that means that V2 equals V3. So V2 equals T. And then the last equation and the second equation both say that V1 equals 0. So a basis for the 0 eigenspace is 0, 1, 1. V2 and V3 are both T. Then let's look at the 2 eigenspace. So we'll solve A minus 2I v equals the 0 vector. So that's, we'll subtract 2 from the diagonal, negative 2, negative 2, negative 2. Copy everything else. So this is our system of equations, right-hand side 0 again. And we can get rid of the 2 and negative 2 here pretty easily, even without changing this first negative 2 to a 1. So we'll let row 2 become row 2 minus row 1, row 3 become row 3 plus row 1, and then we've got negative 2, negative 1, 1, 0. Negative 2 minus negative 2 is 0. Negative 2 minus negative 1 is negative 2 plus 1, which is negative 1. 0 minus 1 is negative 1. And then negative 2 plus 2 is 0. Negative 1 plus 0 is negative 1. 1 minus 2 is negative 1. All right, now we can see that the second and third equations are the same, so let's just get rid of one of them. And this is almost easy enough to solve, but let's multiply both the first and second row by negative 1 to get rid of the negative signs next to the variables we're going to solve for. So row 1 becomes negative row 1, row 2 becomes negative row 2. Then we have 2, 1, negative 1, 0, 0, 1, 1, 0. Alright, so if we let v3 be t, then the second equation says that v2 plus t equals 0, so that means that v2 equals negative t. And then the first equation says that 2v1 plus v2, so it's negative t, minus v3, so minus t, equals 0. So 2v1 equals 2t, so v1 equals t. So a basis is v1 is t, v2 is negative t, v3 is t. So 1, negative 1, 1 would be a good basis. Now let's look at the negative 2 eigenspace. So we'll solve A minus negative 2i, that's A plus 2iv equals 0. And then, so I guess we're adding 2 to the diagonal, 2, 2, 2. And I guess we can do a couple row operations. So let's see. We can let row 2 be row 2 plus row 1. That'll get rid of the negative 2 here, and we can let row 3 be row 3 minus row 1. Then that gives us 2, negative 1, 1, 0. Second row is negative 2 plus 2 is 0, 2 minus 1 is 1, 0 plus 1 is 1. Third row is 2 minus 2 is 0, 0 minus negative 1 is positive 1, 2 minus 1 is 1. Alright, again the third row is just equal to the second row, so let's get rid of it. I think we can solve this as it is. v3 is our free variable, that's t. The second equation says v2 plus v3 equals 0. So that means that v2 is going to be negative t. And then the first equation says that 2v1 minus v2, so that's plus t, plus v3 equals 0. So that's 2v1 equals negative 2t t, or v1 equals negative t. So a basis would be if v1 is negative t and v2 is negative t and v3 is t, these are all multiples of negative 1, negative 1, 1. All right, so let's collect the three bases of the spaces, the eigenspaces. So our eigenvalues are 0, 2, and negative 2. And the bases are for the 0 eigenvalue. We have a basis of 0, 1, 1. For the 2 eigenvalue, we have a basis of 1, negative 1, 1. And for the negative 2 eigenvalue, we have a basis of negative 1, negative 1, 1. Now remember, the natural basis of V is three matrices which have trace 0. There's the 1, 0, 0, negative 1 matrix, and then 0, 1, 0, 0, and then 0, 0, 1, 0. So 0, 1, 1, if we look at this as a coordinate vector, it means 0 times this plus 1 times that plus 1 times that, which is this matrix. 0 this, 1 times that plus 1 times that. Puts a 1 in the 1, 2 position and the 2, 1 position. And then 1, negative 1, 1 means one of these minus one of those plus one of those. So 1 of this minus 1 of that plus 1 of that. And then negative 1, negative 1, 1 means minus this minus that plus 1 of that. So these are bases of the 0 eigenspace, 2 eigenspace, and negative 2 eigenspace of T in the vector space V. So that's a 0 eigenspace vector, basis vector. This is a 2 eigenspace basis vector, and this is a negative 2 eigenspace basis vector. Let's check. So remember, T maps a matrix M to the all ones matrix times M minus M times the all ones matrix. So T of 0, 1, 1, 0 is the all ones matrix times that minus that times the all ones matrix. So if we multiply out, we get 1, 1, 1, 1 minus 1, 1, 1, 1, which is the 0 matrix, which is good because we expected to get 0 times this matrix when we applied T to it. Now let's see what happens if we apply T to that matrix and see if we get 2 times it. T times 1, negative 1, 1, negative 1 is the all ones matrix times 1, negative 1, 1, negative 1 minus 1, negative 1, 1, negative 1 times the all ones matrix, which is 2, negative 2, 2, negative 2 minus 0, 0, 0, 0. So that's 2, negative 2, 2, negative 2, which is good because we were expecting to get 2 times this matrix when we applied t to this matrix. Finally, let's see what happens when we apply t to this matrix. Make sure we get negative 2 times it. T times negative 1, negative 1, 1, 1 is the all ones matrix times it minus it times the all ones matrix. We get 0, 0, 0, 0 minus negative 2, negative 2, 2, 2, which is positive 2, positive 2, negative 2, negative 2, which is good because this is negative 2 times that matrix, which is what we expected when we applied t to this matrix. Right, now finally, what is the matrix of t with respect to this basis of, not the natural basis, but this basis of eigenvectors? Well, these eigenvectors all have different eigenvalues. That means that they're linearly independent, so they do make a basis. Well, the first column is, let's call this basis C. So 0, 1, 1, 0. 1, negative 1, 1, negative 1, and negative 1, negative 1, 1, 1. So the first column is the coordinate vector of t of, let's call these W1, W2, W3. The coordinate vector of t of W1 with respect to C. So t of W1 equals 0 times W1. And 0 times W1 is 0 of this plus 0 of that times 0 of the other thing plus 0 of the other thing. All right, now the second column is the coordinate vector of t of W2 with respect to C. Well, t of W2 is 2 times W2 because it's an eigenvector with eigenvalue 2. So that means it's 0 times this plus 2 times itself plus 0 times the other thing. Coordinate vector is 0, 2, 0. Now the third column is the coordinate vector of t of W3 with respect to C. T of W3 is negative 2 times W3 because it's an eigenvector with eigenvalue 2. So that means it's 0 times this plus 0 times that plus negative 2 times itself. The coordinate vector is 0, 0, negative 2. So this is the matrix of T with respect to the basis C of eigenvectors. And you can see it has a nice form. Since we chose eigenvectors, T of every basis element is just a multiple of itself. So we don't have any non-zero numbers except possibly on the diagonal. The end.